Now that we know a little bit about standing waves on guitar strings, let's take a look at standing waves in tubes. Now, in this particular situation, we have an open tube, and many musical instruments are like this, where they're open on both ends. So, for example, we have this nice little piece of pipe. All right, it's a tube, and this makes certain frequencies, and I'd like to understand how that happens. Well, within the tube itself, instead of a standing wave like on a string, standing waves actually are propagated within the tube. So if we were to take and vibrate and make a sound into the tube, we can actually play it. If I purse my lips and then change the frequency a little bit. So as you blow into the tube itself, you can actually turn it into a musical instrument. That's basically what a trumpet is, or whatever instrument that happens to be. Now, open tube means that it's open on both ends. So here and then here, the air is free to move and vibrate at that point. So if we look on the ends of the tube, the air actually moves here and vibrates up and down freely. So in the center, though, if we look, as the wave is propagated within the tube, we've got ourselves a node. So on this particular set, we've got antinode here, and then a node there. Now let's take a look at the wave. All right, we know that if we start out here, one wave kind of looks like this. We start out here, end up here, and it kind of looks like that. Well, let's see what we've got in this particular situation. We start out at the top, we go to the middle, and then end up on the bottom. So we start out on the top, go to the middle right here, and then end up on the bottom. So from here down to here, how much of a wave do we actually have? Well, if you can see it, we've actually got ourselves half a wave again. All right, so we start top to the bottom, that's only half the wave. We don't have this piece, we don't have that piece. So the length of the tube is once again related to 1/2 divided by the wavelength. We can replace the wavelength, so we also go back to some of our old friends. We've got V divided by F with a 2 in the bottom. The good news about this one, obviously, is, well, haven't we seen this before? So an open tube, the same formula applies for an open tube instrument as a guitar string. All right, now, if we draw the next one, all right, let's draw the second, this is called the first harmonic, or the fundamental, or first harmonic. All right, our next one, obviously, is going to be the second harmonic. So let's see if we can draw that. So we've got ourselves a nice little tube here, something along those lines like so. And if we draw that particular one, we're going to put dot about 1/3 of the way here and about 1/3 of the way here. All right, now, when the wave is propagated, remember the ends of the tube are open, so the air is free to move up and down. So always at the end, you're always going to see an antinode. All right, so we start out here, go down through this spot, come back up, and then back to the antinode on the end. Now remember, the wave is moving up and down, so I'm going to draw the other side of it here like so. Moves up, kind of down like this, and we've got ourselves an antinode on the end, antinode on the end, and an antinode in the center, like so. All right, now, if we look at this particular one, we call this the second harmonic. Or also referred to as the first overtone. Okay, so as we look through here, let's check out what our length is. So the length of the tube itself from here to here, all right, is equal to, well, let's see how much of a wave we actually have this time. So when we look at this, waves start out in the middle, it goes down like this, back up like so. All right, let's draw a little midline. So we go from here, 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 all right, like so. All right, now we start out at the top, so we position ourselves here. Then we go down to the bottom, like here. Then all the way back up to the peak again, like so. All right, let's see how much of a wave we got. So we go from quarter here, another quarter here, another quarter here, another quarter there. if I add all those up, guess what? I've got myself a full wave again. So from here, all the way to the midline is 1/4 of the way, another fourth to the bottom, fourth here, and another fourth from there all the way back up to there again. It's one wavelength. It's true. If you don't believe me, draw it out. Okay, now we also know that L is going to be equal to, instead of writing lambda, we're going to write V divided by F. So we have it in terms of that. Voila, we've got ourselves the exact same formula once again. All right, now, if we look, we can draw the next harmonic, okay, which would be the third harmonic. I'd like you to draw that out on your own paper. So construct yourself a tube. Give yourself enough room. Okay, make sure you've got antinodes on the end, and then take a look inside and then see what you have. So we're going to have, instead of 2 dots on the center, we're going to have 3. Yeah, like so. Oops, didn't do a very good job with that one. All right, now it's time to draw our little waveforms like so. Start out antinode down, coming back up, down, and then back up. I hope you did a better job than I did. All right, here goes nothing. And then coming back up like this, coming back down, and voila, there is our third harmonic. Try to draw it, be careful, do the best you possibly can. If we go back through, we can see that this wave starts at the bottom, starts at the top, goes to the bottom, back to the top, back to the bottom, and we end up once again with 3/2 of a wave. L is going to end up being equal to 3/2 V divided by F. And these open tubes follow the same pattern, and we can go back to our generalized formula. We put the harmonic in, first, second, third, fourth, whatever it is, divide by 2, V divided by F. Now we can handle any harmonic that we would like to. So is there a fourth harmonic, a fifth, a sixth for open tubes? You sure got to believe it.